In this video, we want to illustrate another concept for circuit simplification, and it turns out it can be a very handy concept in substitution to use. So what we want to talk about is we want to talk about source transformation. I can get a pen going here. We want to talk about source transformation. Now, source transformation comes about by something we mentioned early in the semester, terminal pair equivalence. So we make a lot of substitutions and things in circuits in order to make them easier to solve. It's extremely important that when we do that, we think as we make our substitution about terminal pair equivalence. So here's a couple of circuits, and I just put them in boxes. So I have circuit 1 and circuit 2. And circuit 1 is connected to terminals A and B. Circuit 2 is connected to terminals A prime and B prime. So these two circuits are equivalent at the terminal pairs AB, the equivalent at AB, in other words, A prime, B prime, if whatever we place at A and B produces the same terminal voltage and input current at A prime, B prime, then the circuits 1 and 2 are called terminal pair equivalents. Now we have already done this. When we do a resistor simplification and we take, for example, a couple of resistors that are in parallel and we substitute those with the equivalent parallel resistance, we've, for all practical purposes, found a terminal pair equivalent. So it turns out it's possible to do this in the case where you have a voltage source in series with a resistor that can actually be replaced with a terminal pair equivalent of a current source in parallel, what am I doing here? A current source in parallel with that same resistor. So these two circuits are called terminal pair equivalents. And notice that the arrow on the current source points in the direction of the positive polarity of the voltage source in the terminal pair equivalent circuit. In this case, we have terminal pair equivalents, and I'll call this R prime, and I'll call this I prime. We have terminal pair equivalence if I prime is V over R and R prime is equal to R. So, for example, if you have 10 volts and 2 ohms, that can be replaced with a current source 10 over 2 or 5 amps in parallel with that 2 ohm resistor. And it works backwards. So if you started with this circuit, you would take I times R, multiply together to get V, and you would just carry your 2 ohm resistor to the other circuit. Okay, you can either show those terminals like this, or you can show them like this, whichever makes, this is all one node, so just whichever geometrically makes the most sense. So that is a source transformation. It's going to turn out to be extremely useful and handy in solving some circuits. So what I think I want to do is, if I can locate that circuit that we worked for superposition, I think should have that. Let's see if I can't. Nope. We'll go back to it and we'll go back to that circuit that we just solved. Where was that? Yeah, this is the one I want. Okay. Sorry, my pen is in too close of a proximity, so let me copy that, and then we'll paste. It's not wanting to do the paste. There we go. All right, so we're going to look at this circuit because this is actually a prime candidate circuit for using superposition. I'm sorry, for using source transformation. So let's pull up a color pen. And remember, in that example, we worked with superposition. We wanted this voltage across the 2-ohm resistor, and so we used superposition to do that. I just want to rework this problem using source transformation because I think you'll see how much easier it is. And what I think I want to work with is, let me see. I think I want to work with doing the source transformation on the 16 amp current source and the 5-ohm resistor. So for now, and I want to go ahead and combine the 6-ohm and the 3-ohm that are over here with this 30-volt source. So here's my 30 volts. That's 6 and 3 combined together to give 9 ohms. That's the one I kept seeing wrong in the previous example. Here's my 2 ohms. There's the voltage I want. Here's the 8. Here's the 4. And now what I want to do is I want to replace this parallel combination of the current source and the 5-ohm resistor with a voltage source in series. So what you do is you find your terminal pair, and then you find it in your new circuit. And it is between these two terminals that you're going to have your replacement of a resistor in series with a voltage source. Okay, and that voltage source is going to be I times R, so it's going to be 16 times 5 or 80 volts. Okay, now wow, things just got a lot simpler. Here's my 30 and my 9, my 2, and now adding all of these together, here's my 17 ohms again. Here's my 80 volts. And here's the voltage that I want. Now, if you want to get really fancy, okay, you realize you can do a source transformation here and here. So starting with this one, that'll be a current source, 30 over 9, in parallel with that 9 ohm resistor. And then I've still got my 2 ohm resistor. And now here I will have another current source, this time it'll be 80 over 17. And wow, did that ever simplify things, okay? So now I have two choices. I can combine everything except the 2 ohm resistor and do current divider, or I can realize that this is now a single node circuit and I can write a single node equation and solve for V1. Since we already kind of did that, let's practice with combining circuits, it's combining current sources and resistors. So I have two current sources. They're both pointed up. So I can add those two, and that'll just be 30 over 9 plus 80 over 17. And then I have two resistors here, the 9 ohm and the 17 ohm. So I can combine those in parallel. And then here is my 2 ohm resistor left completely alone, and that's the voltage that I want. So if I want to add that 30 over 9 plus 80 over 17, I get, we'll call it 8 amps. There's a little bit of a decimal, but we'll round that off. 9 times 17 divided by 26, that's 5.8 ohms here. So now super easy to find this current. I is 5.8 over 5.8 plus 2 times 8. And remembering, I saw this on the exam, remember that you can only do current divider on one pair of resistors at a time. So if I do this, I'm getting 6.04 amps. Multiplying that, I can get the voltage 6.04 times 2. I don't think that's what we got in the previous method of working the problem, so I'm guessing I made an algebra error, probably in the superposition, because this looks correct to me. Okay, so so that is an illustration of how you would use source transformation. We could have done this another way. So at this point, I want to try to show you why we would not. Let's see if I can't. I want to show you why we would not have done it with the other option, which is taking that. Yeah, it just doesn't want to keep that in its memory. So let's go back and find that circuit again. Copy. And all right, so let's find the circuit again. Now you might be saying, well, look, why did you start out with your simplification by working on this current source in parallel with the 5 ohm resistor? Why didn't you come over here where you had a voltage source in series and instead start there? So if I had done that, I would have this, and then I would have 2 ohms and ... the rest of the circuit. And I could have done that, but it doesn't really buy me anything, because I don't want to combine these two in parallel. I would get the same voltage because it is a single node. So I guess my comment here is that unlike node voltage or mesh current, when you start using things like superposition or especially source transformation, there's no clear methodology for how to pick where to start if you're going to solve the circuit completely with source transformation. So what I recommend is that you use source transformation as a way to reduce the number of nodes and or meshes and or change the type of source you have, so that you make the node voltage or mesh current method easier with fewer equations. And that in the process of doing those terminal pair equivalent substitutions, you do not eliminate the resistor that you're trying to find, or the element that has the variable you're trying to solve for. So in this case, we would like to keep this 2 ohm resistor intact because that's the resistor we wanted the voltage across. So like illustrated in the previous problem, I might not actually do all of those steps. I might get this circuit down to where I had 2 meshes and then write a set of mesh equations, because then I've got a 2 variable, 2 unknown, 2 equation kind of problem. So that's my recommendation to beginners in circuits trying to apply source transformation. Yes, you can use source transformation really to eliminate all the way down to the variable that you want to solve for. But once again, in circuits, our overall approach is efficiency and expediency. So it may be more efficient to do one source transformation, and then rather than try to do repeated ones like I just showed in the previous example, probably easier to stop at some point and say, okay, now I've got 2 meshes, 2 voltage sources. Let me write 2 mesh equations and get a solution. So really that's kind of a matter of personal choice unless you're specifically asked to do something using source transformation. But